Okay, so we keep going on the table summarize. And then the following properties here, the most important thing is the first one is our dynamic viscosity. And then we use the mu. And then the second is the kinematic viscosity. We use the nu. Okay? And you can see there is certain definitions for the dynamic viscosity is a property that characterize the resistance to shear stress and the fluid friction. So I always emphasize the viscosity is a kind of the friction force caused by the fluid and the boundary between the fluid and the solid. Okay? So, and then this is show the units of the dynamic viscosity. And after we define the dynamic equation, so you will understand what's the units of the dynamics. But right now it's very important. We would like to discuss the viscosity response to the effects of the temperature and the pressure. This is very complicated, so you need to wake up to have more power to understand what the meanings. So the first, we can see the temperature increase. Okay, temperature increase and the dynamic viscosity also increase. We actually know because the figures in the previous slide, you see the patterns. When the temperature increase and the viscosity will increase also, especially for the gas. Okay, so it's very important. That's why the reason why the temperature increase, and we can provide additional energy on the systems. And the additional energies will provide and support the gas molecules particle to move. Because if there is no energy and the molecules of the gas just randomly distributions on the environment, but if you increase the temperature, so there is additional energy powers to support the gas can more frequently moving. And the more frequently movings will have high probability to collision together, right? And if the gas molecules collision together, will increase the viscosity. Okay, so the idea is for the temperature increase and the interaction force between two molecules will increase. That will also result in the viscosity increase. Okay, so that's why the reasons the temperature increase and then the viscosity also increase, especially for the gas. But if you see the temperature increase in here but the viscosity will decrease, especially for the liquid. So if we consider the liquid, the definition is the liquid, there is a certain interaction force between two molecules for the liquid, right? The certain definition is that. So if you provide additional energy will broken the connections between two molecules. So for the liquid, if you increase the temperature, the additional energy will provide to break the connection between two molecules. So that's why the viscosity will decrease. Okay, so it's a totally different trend. And the two response associated with the temperature already shown on the figures. As we discussed on the previous slide, we have the figures, and we see the curvature line have a different trend. One is the positive trend, another is a negative trend. Okay, so the negative trend is for the liquid because the temperature increase and the viscosity will decrease. But for the gas, the temperature increase, but the viscosity will increase also. Okay, so it's a table very good and summarize some idea on the table, but which we are trying to figure out on class. What are the physical meanings? Okay, and the second target here, we are trying to discuss the viscosity with the pressure changes. Okay, so it's a very good. Either the gas or the liquid are idealized with the viscosity independent of the pressure. Okay, so two material, the gas and the liquid, are independent of the pressures for the dynamic viscosity. Okay, so that's because that means even though the temperature increase or decrease, but there is no response, and cannot affect the viscosity of the two material. Okay, so right now we are moving to the kinematic viscosity. As we remember, the kinematic viscosity it is defined by the ratios of the dynamic viscosity with the density. Okay, so you should consider additional properties involved in our definitions of the kinematic viscosity. Okay, so we are trying to, based on the equation showing here, and reconsider how responds to the temperature and the pressures. Okay, so we take a look at the first, and then we still focus on the gas. Again, so temperature increase will result in the viscosity increase. But that is for the kinematic, right? Kinematic viscosity. So what are the reasons? So you see, we know that the mu will increase when the temperature increase for the gas. And we also know the density, when the temperature increase, the density will decrease, right? And we know that the nu is defined by the mu, a ratio between the mu and the rho. So the bottom is decreased and the top is increased. So that's the reason why the kinematic viscosity will increase also. Okay, so that makes sense. And when we discuss with the temperature here, increase also, but right now we are looking for the liquid material. So we reconsider the condition for the liquid. So again, when the temperature increase, but the viscosity will decrease, right? This is for the liquid. And we still know the density will also decrease. So if we go back to see the definitions of the nu is equal to the mu divided the rho, we cannot decide the result kinematic viscosity is increase or decrease, because either the top mu and the bottom rho are also has the decreasing response. So we cannot identify its increase or decrease for the kinematic viscosity. So for this result, we should remember, I tell you a result, the kinematic will decrease. That indicates the dynamic viscosity here will decrease a lot compared to the density. And the result, the kinematic viscosity will decrease also. Okay? The dynamic viscosity will decrease a lot compared to the density. So that result, the kinematic viscosity will also decrease. Okay? And then we are trying to discuss the response for the pressure effect. Okay, so we are moving in here. And before I introduce the why, the reasons, here you should, you can see there are some corrections by myself. Because the original in the textbook, here is the typo errors. So I make the corrections. So the result indicates the pressure increase. Here, we have the pressure increase and the result, the kinematic viscosity decrease. And then you go back to consider because the mu didn't change when the pressure changed, right? Because the baseline idea in here, the mu is independent of the pressures. So that didn't change. But what's the density? The density for the gas, the pressure increase, the density will increase also, right? As you remember, our previous exercise tells us if we do the compressions and the density of the air will increase also. So that's based on the mu divide is equal to the ratio of the mu to the density, because the density will increase but the mu didn't change. So that will result in the kinematic viscosity decrease. Okay, but the button here for the liquid is keep. There is still no response with the pressure because the density for the liquid is very difficult to compress. So even though you increase the pressure, but the density didn't change a lot. So that's why we still independent here of the pressures for the liquid. Okay, so even though the table just summarize some sentence on the table, but we can try to figure out the reason why based on our knowledge. Okay, so that's why I can figure out there is a typo error on the textbook because I know the density will increase will result in the viscosity decrease. So I can make the corrections on the tables. Okay, and then the following properties, we call that the surface tension, the vapor pressure, and the bulk modulus. Will have the more discussion in the following slide. So I'm not going detail in here, but you can just take a quick look for how the response for the temperature of the surface tension and how response for the vapor pressures. Okay, so I'm not going details, but the right hand side I'm showing here, I just highlight if you meet some problem trying to calculate how large of the kinematic viscosity. The first idea, you should find in the density first, okay? Especially for the gas, you should apply the ideal gas law. And you have the density, and you can check the table to have the mu values for the different conditions. Then you can calculate the kinematic viscosity. Why I highlight here, because sometimes the table didn't summarize the kinematic viscosity values with a different condition. The table only summarizes some mu and only provide the law. Okay, so you need to calculate the kinematic viscosity by yourself based on your knowledge. Okay, so we need to move to the next slide. And the next slide just summarize some important properties for the specific gas. Okay, so how important it is, we have the density, and we have the kinematic viscosity, and we have the gas constant. And the final properties, we call that is the heat. This is a new properties, specific heat. Okay, and this is the ratios. We call that the adiabatic exponent ratios I defined in here. But the final two parameters shown here are not important for our class because in our class we do not looking for the problem associated with the thermal problem. Okay, so in this semester, the material I am focused on the fluid problems. Okay, but you can see there are some important gas, the air and the CO2 and the helium and the hydrogen and the methane and the nitrogen and the oxygens. So all the important gas you can check from the table for the physical property like the density and the kinematic viscosity. So this is a table very important if in the future you are deal with the problem with the different gas, you can check from the table. Because when we solving the problem, we should know the property first. And sometimes the questions will let you to answer what the property we have in the problem. Okay, so you can double check from the tables. Okay, this is also good tables. It just show the physical properties, and the target is the air, and especially under the standard atmosphere's pressures. That indicates the pressure we will keep in 1 atm. This is keep the pressure, but we see a different response of the temperature. So you see here, the temperature going down is increased pattern, right? So we can see how response when the temperature increase, how response of the physical properties. So again, you can see for the density, when the temperature increase, we will see the density decrease, right? And the similar patterns on the specific weight also decrease when the temperature increase. But we see this is for the gas and the air. So we see, you can see the dynamic viscosity will increase a lot. A little bit, not a lot, a little bit when the temperature increase. Okay? And the kinematic viscosity also increase when the temperature increase. So the two currents, the trend showing here is consistent with the table. It's consistent with the table showing here. Okay? So sometimes you can double check is correct or not. Just double check the information summarized on the tables, and you can based on the table list in here to double check the idea. Okay, so I just put one slide in here, just trying to describe the idea again. So you can see in these figures, we have the problem. What's the problem? We know the system. What is the system? The system in here, we can figure out the system. What the system is the air in tank, right? So we have the air in the tank in here. And then ambient through a horizontal pipe. So the air is held outside. Okay? And then we know that the air speed is the 10 meters per second. And there are some friction factors and the length of the pipe. Okay? So this is the property we have. This is the property we have. And you can see some property is corresponding to the kinematic property, right? Because we are looking for the velocity. And some properties we are looking for, this is the pipe length. Okay, the pipe length. But what's our major properties? Because this is the problem we involve the system is the air. Okay, so we should know the density of the air. So before we know the density of the air, we should double check the condition. That's why I say the state. We should state our conditions. And the condition is 20 degrees and at the 1 atmosphere pressures. So if I have the table I can check the density of the air. I can check the density of the air. Okay, so sometimes I will provide you the table or the figures, or I directly provide you the answers, the number values. So when we look for the problem, we don't worry. We are not worried because we can look for what's the system and what the system topic, and then what's the equation we need, and what's the physical property we need. And we collect all the information, and then we can re-look the questions and trying to figure out the solutions. Okay, so right now I'm not going detail for the questions because this is out of our range in teaching right now. And in the following class, you will know what the correction factor alpha and how can we deal the problem in here, showing here. Okay, so then in the following slides, I will show some topic related to the density. So the first one, we just provide a certain definition of the specific gravity. So we can see the specific gravity is defined as the ratio of the density of the material to the density of the reference material. So most important is what is the reference material when we compute the specific gravity. So you see here, I have highlighted the reference material is the water, but at the 4-degree conditions. Okay, so we know the water, okay, but the water will change the density under a different temperature. So our reference density, when we compute the specific gravity, Sg, and we will base on the condition at the 4-degree. Okay, this is very important. And actually, overall, the Sg, if you compute the Sg, is less than 1, that indicates the material will often float on the water because the reference is the water. Okay, and then if the larger than 1, it indicates that generally will sink. Okay, it's a common sense. But we will define some special case. We call that the miscible and the immiscible. It's oil and the alcohol, the difference. Okay, so sometimes the liquid will miscible or immiscible with the water. So you cannot only based on the Sg values to identify it's floating or sinking. Okay, it's based on some material property difference. Okay, so I just highlight some important material for the Sg value in here. Like the petroleum product is around the number in here, and the seawater is 1.3, and the mercury is 13.6, and the steel and the aluminum and the concrete is especially material for our engineering structures. Okay, so it's still difficult to remember, but you should have some images, what the ranges for the different material. Okay, so again, we say more, and then we will have the exercise to practice and realize the idea I have teach before. Okay, so this is an exercise. So first, we should take a look what's the problem. Okay, so we actually know the gamma, the mercury. Okay, the gamma mercury, the specific weight is equal to the 133 kilo Newton per meter cubic, right? Okay, and what's the problem we need to answer is calculate the density first and the specific gravity. So we don't know the density. So this is our first unknown parameters. And the second is specific gravity. Okay, so this is our two properties we need to answer. And usually the specific gravity, we call that the SG. So we need to answer the two unknown parameters. One is the density, another is the SG values. Okay, so we based on the specific weight equation, we know that the gamma will equal to a rho G. So the first problem is quite simple. We just compute the rho is equal to the gamma divided the one gravity, right? It's a very simple idea. So we just put the number is the gamma is the 1, 3, 3, and the 10, 3 powers. And the dimensional unit is the Newton per meter cubic. And we should divide it, the gravity is 9.81, and the meter second square. Okay? And then because we would like to compute the answer is the density, okay? So you can make the dimensional consistence. Okay, so use your calculator to compute the answer by yourself. And for me, the density is equal to the 1, 3, 1, 3, and 5, 7.6 around. Okay, around. So the unit is kilogram per meter cubic. But it is not our only the purpose, because we are trying to compute the specific gravity. And as I mentioned, the specific gravity is a ratio. We have a rho, okay? It's our ratio of the specific density to the density of the reference material. So our density of the reference material is the water at the 4 degrees. And as I remember, the water at the 4 degrees, the density will equal to the 998 kilogram per meter cubic. Okay, so I can compute the specific gravity based on the two density values here. So we have a 13557.6 and divided the 998. And because all are the density, so the units will directly cancel out. So we know that the SG is dimensional less parameters. There is no dimensional. So you can base on your calculator to calculate the final answers. So this is about, the answer is 13.6, and then there is no dimensional, so we don't need to put the unit. Okay, we don't need to put the unit. So it's a very simple idea. If we know the certain definitions of the physical property, and then we can calculate the value very quickly. Okay, so, and the only unknown parameter is we didn't know. If we didn't know the reference material density, you cannot compute the SG value. So in that value, you should keep in mind, especially for the reference material density in here, is a 998. Okay, for our problem. And then another topic related to the density, sometimes we will always call that the liquid cannot compress. Okay, so this is, we call that the constant density assumptions. We assume the liquid cannot be compressed. So we call that is incompressible flow. Incompressible flow. So it's for the liquid, especially for the water. Okay? But for the gas, you cannot always say the gas cannot compress. Because as I showed, one example is the material is the air. And we know that the air, certainly we can compress the air. and change the volumes and the density will increase. Why I can say the constant density? It's not the truth, right? So especially for the gas, and I tell you in the steady flow, what is the steady flow? That indicates the property didn't change with the time. So I call that the steady state. So if the gas in steady flow, that means the property didn't change with the time, and the result of the density is assumed to be a constant. But you should satisfy the certain condition is the Maher number is less than the 0.3. So what's the Maher number as we learned before in our high school? You can see junior high school or senior. You can see the Maher number is the ratio of the fluid speed to the speed of the sound. So it's the fluid speed relatively to the sound speed. And if the ratio less than 0.3 and under the steady state, you can say the gas also is in compressible flow. If not, you cannot say, because we certainly know the air can be compressed. Okay, so this is a slide just summarize maybe all the fluid we can assume in compressible flow, especially for the water. But for the gas, you should consider your condition can be validated. So I show the one condition you should satisfy is the Maher number is less than 0.3. Okay, so and then the slide just put the information of the Buck modulus. Okay, as I always emphasize, the Buck modulus can be used to identify the fluid compressibility. That indicates the Buck modulus will provide you the information to identify the fluid is compressible or not. Okay, so you can see the certain definition of the Buck modulus is the pressure difference. It's the ratios of the pressure difference to the relatively volume changes. To the relatively the volume changes. Okay, so what are the meanings? If we consider, so we need to define our system. If we consider right now we under the compress. Okay, we under the compress process. Okay, and then we can have the before and the after, right? So we can define the state is the before compress and after the compress. So this is our state 1. And the after is our state 2. And then we will have the pressure, right? Because of the state, we should providing the certain physical values, property values for our system conditions. So we have a P1 is a pressure before the compress, and then we may have the V1 is the volumes, and we may have a different temperature is the T1, right? And for the state 2, I can use the symbol is the P2, V2, and the T2. So what are the pressure difference? So if we will compute the delta P, I will use the P2 minus the P1. And because right now our system is under compressed process, so that indicates the P1 always larger than P2 is always larger than P1. So the sign in here is the positive, right? Because the P2 is larger than P1. Okay? And what the volume changes, we know that the delta V, I will put the V2 minus the V1, right? And I assume the material can be compressed. So that indicates the volume 2 is less than volume 1, right? Because the material can be compressed. So the sign here should be a negative. Okay, so if you go back to see the certain definition in here, the delta P is positive, but the delta V is negative. And then you can notice that there is additional negative sign here. That's because usually we assume the compressed process, so the delta P is positive. But the resulting volume change is negative. So we are wondering to keep the positive Buck modulus. So there is additional minus here. Okay, that's the reason why you can see the definition of the Buck modulus. There is additional negative sign in here. Okay, so this is the reason we define the Buck modulus based on these equations. Okay, so there are some properties and we are trying to prove. As you can see, the system condition for an ideal gas and based on the isothermal process, I tell you the Buck modulus finally is equal to the P. Okay, the finally is equal to the P. What is the P? P is the environment pressure. P is the environment pressure. So in other words, I can tell you the EV will equal to the P2 because the P2 is our final environment pressure after the compressed process. So in here, I'm wondering to prove the equation EV is equal to P2. So how can I do to the proof? So we can step by step to prove these problems. So you can see I can use the ideal gas law. Okay. So first I have the ideal gas law. So I know that the P1V1 will equal to the mole number multiply the gas constants and the temperature 1, right? And I assume the containers inside the mole number didn't dissipate. So the mole number is the same and the gas constant didn't change. Okay, and I know that the P2 also the V2 will equal to the mole number multiplied R and the T2. Okay, so what is the isothermal process? So in here we based on the isothermal process. So we actually know the result is the T is equal to Ty and equal to T2, right? Because the temperature didn't change when the process doing. Okay. So this is why I have the conditions. And I rewrite the equation to be the P1 will equal to the V1 and the nRT, okay? And the P2 will equal to the nRT divided the V2. So I would like to compute the delta P, okay? And as I mentioned, the delta P is the P2 minus the P1. So I just the following two equations showing here. I take the same parameter outside, and the inside I only have the V2 over 1 minus the V1 over 1, okay? And I can reorganize the equation to be the V1, V2, and the top is the V1 minus the V2. Okay, so I take the V1, V2 outside. So I rewrite the delta P will equal to the nRT divided the V1, V2. And the inside, I only have a V1 minus the V2, right? Okay, and I actually know the V1, V2 will equal to the minus delta V, okay? So here I can rewrite the nRT divided the V1, V2. and minus delta V. Okay? So if you do the comparison between the certain definitions on here, you can reorganize the equation. So I wondering to have the bulk modulus equations. Okay, so you can see I can reorganize the delta P, and I can divide the minus delta V here. I just move the right hand side parameter to the left hand side, and I need to the additional V, right? This is V is initial volumes, so this is V1. So I can also put the V1 in here, okay? Because there is a V1 in here. Okay, so on the right hand side, I only have the nRT divided the V2, right? I only have nRT divided the V2. And the left hand side is the bulk modulus. Here is already the bulk modulus. So finally, I can tell you the nRT divided V2 in here is in here. nRT divided the V2 will equal to the P2, right? So I prove the bulk modulus for the ideal gas will equal to the environment pressures, P2. So in the future, if you're looking for the problem discussing with the ideal gas, and the bulk modulus is equal to the environment pressure, and you don't need to compute anything. You know that the EV will equal to P2. Okay, so this is especially for the ideal gas. Okay, so indicate if not the material is not the ideal gas, you cannot apply these equations. Okay, so you should based on the original bulk modulus equation here to calculate the bulk modulus. Okay, and in the following, I just also put some important idea. Even though the compression or expansions, but under adiabatic process, the EV will always equal to the Kp. And the K in here, I already highlight is the adiabatic exponent values. Okay, adiabatic exponent values. So, but sometimes in fluid mechanism, we don't touch the topic related to thermal problem. So just keep in mind, but in the future, you may meet some thermal problem. You should apply the K number in here. Okay, so usually we say too much, so we need to the exercise to review all what we learned before. So this is maybe our final exercise today, and we're trying to figure out what's the major problem in here. Okay, so as I mentioned, for the first you have the problem, you should consider what's the system we have. So in here, what's the system? The system, the topic is the liquid, okay? It's the liquid water. And we actually know the liquid water, the volumes initially is the 1 liter. And we know the 1 liter will equal to the 10 minus 3 power cubic meter, okay? So this is right now the system target is the liquid water. And what is the state? So the second we state some important informations. So we know that this is isothermal compressions. Okay, so we know that this is isothermal compressions. And what are the compressions we have the pressures? So you see what's the pressure? The pressure after the compressions, then this is the from atmosphere. So the atmosphere is our initial pressure, right? So we compress the atmosphere pressure into a pressures of the 1 million par. And this pressure is the absolute pressure. Okay, because we do the isothermal compressions. So the problem we require to answer the property is how change it. What is the change? So it's the change in volume of water. The change in volume of water. So we know that the delta V is our unknown parameter. We didn't know. So when we see the case in here for the problem, we may exciting because when we look for the isothermal, we are very exciting because the previous slide tells us the EV will equal to the P2, right? If we know the P2 in here, so that means we can directly to say the EV is equal to P2, and that's all. And we have the EV, so we can recalculate the delta V, how large it is, right? But not correct, because this system is for the liquid water. But this idea, the sentence equation showing here, only satisfy for the gas. So here, we cannot apply this idea. So we go back to see the problem. So how can we know the EV for the water? So we should check from the table. And then we can find out the EV value in here. So you can see I write down the EV value in here for the water. So in the future, you may remember these numbers, especially for the water. So if for this problem, we didn't know the EV of the water, we cannot continue the problems, okay, solving the problem. So we know that the EV of the water will equal to the 2.2 giga newtons per meter square. Okay, if we don't have the EV, we cannot keep going the problem solving. Okay, and then we go back to think. We know that the EV should be equal to the minus delta P and divided the delta V and also divided the initial volume, right? The V. Okay, so we can just try to reorganize maybe because the delta V is our unknown parameter. So I can know the delta P multiply the initial volumes and divided the EV, and I can compute the delta V. So the first, we should know what is the delta P in our systems. So we first compute. So first we compute the delta P will equal to the P2 minus the P1. Okay, P2 minus the P1. So we know that the P2 is the 1 million par. Par is the Newton per meter square. And then minus the 1 atmosphere. Okay, 1 atmosphere, where we know that 1 atmosphere is here. Okay, in here. So we can write down it's 101.3 and 1,000 multiply 1,000 K Newton meter per meter square. So you can use your calculator to compute the answer. What's the answer for this number? So it's around the 898 and 700 Newton per meter square. Okay, this is a delta P. And because we should know the initial volume is the 10 minus 3 meter cubic. And the third, we know that the EV, okay, we already know. So we check all the value we have, and we put back to the equation 1. Okay, we put all of the values, go back to the equation 1. So we have the equation 1 will rewrite to the delta V will equal to the minus delta P. Delta P is 898,700 Newton meter square. And the initial volume is 10 minus 3 powers meter cubic. Okay? And we should divide it, the bulk modulus is 2.2 10 powers, and the unit is Newton and per meter square. So it's a very huge number, so you should calculate the value, be careful by your calculators. So for me, I trying to recalculate the number right now. Okay. And so the values in here, I should write down the minus 4.085 and the 10 minus 7 meter cubic. Okay, this is my final solutions for these problems. So usually I tell you, after you compute the solution, you should review your answers. It's make sense or not. And I always emphasize the liquid is very difficult to compress, right? As you see the result, it makes sense because the volume change is quite smaller compared to the true. Initially, our initial volume is 1 liter. So you only have a little bit volume change after you do very large pressure compressions, but no significant volume change after your compressions. Okay, that's why the reason usually we tell you the water liquid cannot be compressed. So the volume didn't change when you do the compress process. Okay, and in the past, when the student just write down the answers, you just provide the answer, no, nothing changed, because the professor teacher tell me the liquid cannot compress. And then finally, I just give him the grade because it is an idea. But for our quiz, you should write down the answer and make the comment. You cannot directly to say yes, no, because the professor say the liquid cannot compress. Okay, so maybe today I just stop here, and